Annyeonghaseyo, Korea. It is a pleasure to be here with all of you and an honor to represent New World and share with you the game that we have built in the cloud utilizing AWS. My name is Matthew Wu, and I'm a software development engineer for the backend team on New World. I've been on the New World team for over 6 years, and in that time, I've worked on a variety of the backend, including the C++ server, the control plane, and the microservices that surround and support the game. As a fun fact, when I first started on the New World team, I actually started on the UI team. Now, what is New World? Let's take a look at this video.
I am the myth. I am the glory you seek. I am the island. And the island is me. I am the rage, the destruction. I am Eternum. And Eternum is me.
New World is a massively multiplayer online game, an MMO where you, as a player, are exploring a mythical new continent called Eternum, which is filled with magical properties. But these magical properties have also corrupted people, and they've corrupted the nature there. You start in this world as a brand new player who has washed up on the shores of Eternum. And you build up your character through completing quests, gathering resources, and leveling up your skills through combat and crafting. You can play in a world with up to 2,500 players in a massive, seamless world. And you can join together in small groups of 5 or larger companies. Action in New World is combat-based, or combat in New World is action-based. So you can block, dodge, as your opponent tries to swing their sword or shoot an arrow. And all this combines in epic 50 versus 50 wars, or smaller 3 versus 3 arenas. Now, here are some statistics about New World, including the peak concurrent users, the peak Twitch viewers, the number of worlds that we ran, and our client request rate. Now, when I tell people that I work on New World, they're often excited to hear that I work on a video game. After all, it sounds like a dream job, as I'm sure you can all attest to. But it's not easy to describe what it means to work on the back end of New World. I think people look at the gameplay of New World and say, wow, did you work on this weapon? Or maybe the modeling of this piece of armor? Or maybe you worked on the reflections and the rendering of the video game. But then I tell them that I work on the back end and I get confused stares. You see, I think most people think about the client and server interacting simply like this, and that must be the back end. But what they don't realize is that behind the gameplay of New World, there's a whole world of servers and services that exist to support the game. If you take a peek behind the curtain of New World, you will see the many AWS services that we're built on. So today, I want to take a peek behind that curtain with you all at what I'm calling the 3 pillars of New World in AWS. The first pillar is the worlds. The second is the control plane. And lastly, we'll look at microservices. So first off, worlds. This is where it all starts, where we run the game and how we host it. Let's take a look at what's in a world. We host our software on EC2. And there are two classes of instances in EC2, the hubs and the reps. There are 7 hubs in a world and 5 reps. And we did early game scale testing to determine what type of instances would best fit the load that we needed. The hubs do a majority of what you imagine a server needs to do. It handles AI, it simulates the physics of the world, and it handles player interactions, among so many other things. So again, when you're dodging from your opponent, These hubs are what are actually simulating that 3D physics. The reps, on the other hand, which stands for remote entry points, are the only communication point in this world with the players. They sort of act like a bastion and like a router. As a bastion, it reduces the attack surface of our overall world so we can focus on the security of these instances primarily. And as a router, it takes the messages from the players and forwards them to the appropriate hub of the 7. Now, all of this takes place within we have instance hubs, which can also dynamically be added to the world to support the instance content of wars and arenas, etc. Now, all of this takes place within a virtual private cloud, or VPC. A VPC is essentially an isolated network from the rest of the internet. So you create gateways and route tables in order to interact with the internet. Within this VPC, we have two subnets, the public subnet and the private subnet. The public is what the public internet can connect to, whereas the private is what it cannot connect to. And we have an internet gateway here to communicate with the clients. And lastly, we use Code Deploy and Systems Manager to get the software onto our instances and to be able to manage them using stop and start, pause commands. Now, let's take a look at world persistence. As an MMO, we need to be saving the state of the world, the players, constantly in order to restore the server after any downtime. Say, for instance, you have to patch your OSs, or there's maintenance to do, or if theoretically your servers crashed for any reason, but I'm sure your servers never crash. For us, we store all of this in DynamoDB. So let's take a look a little bit at DynamoDB. As I'm sure you probably know, DynamoDB is a NoSQL database. This means that each item or entry into the database doesn't have to have the same attribute schema as all the rest. This means that you should be using DynamoDB for known request types rather than the flexible kind of query schema that you get with SQL. And it's built to be compute optimized rather than space optimized. DynamoDB is a serverless database. It's highly available and fault tolerant, and it boasts single-digit millisecond request latency when at load. Now with DynamoDB, normally you will provision the amount of throughput that you need, the amount of read and write capacity. But there's also a nifty version called on-demand capacity, which will scale whatever your usage is. So if you don't know what your usage pattern is, you can use on-demand and later switch to provision throughput with auto-scaling to lower your costs. So what does it look like for New World to use DynamoDB for its persistence? New World, for each entity in New World, it's composed of many different components, the players themselves having over 100. And each of these components have their own persistence schema, which developers are constantly changing. In order to support this flexibility, we serialize all that data into a binary object and put it into DynamoDB. And all of this happens in one table per region. And DynamoDB handles this scale amazingly. In Frankfurt, our largest region, we went from using 100,000 write capacity units, that's 100,000 kilobytes per second written to DynamoDB, to 350,000 within a week of launch. All good servers need logs and metrics. For us, we write to a log file on the instance, and this is uploaded to S3 or CloudWatch. S3, as I'm sure you already know, has highly durable file storage, which makes it a no-brainer for storing files. CloudWatch, on the other hand, makes it easier for us to use CloudWatch Insights to query across a number of different logs for a particular time frame and particular pattern in our logs. Metrics for us go into an internal metrics service, but you could also use CloudWatch for metrics. So now we've added DynamoDB and CloudWatch for writing data to. Now, let me take you back in time and tell you a story about the beginning of New World. When we first started, we started with single instance on-premise servers, which was running both the hub and the rep. But we always knew that we wanted to use the ability to scale out in order to support more load. And when we first started going to these multi-instance servers, we thought, we'll just start with 4 hubs and 1 rep. This would constitute 1 world, but we would need multiple worlds in order to test different builds at the same time. The problem is, to get an operator to manage all these worlds, these instances and connections is a nightmare. As great as the AWS console is, nobody wants to manage even 20 instances by hand. This is where the control plane comes in. The control plane is what allows us to manage all these worlds, all the instances and the connections that are involved. So here, where we have the operator, we replace it with the control plane, and we can issue a command quite simply by saying, create a new world. No pun intended. But we can also do many other operations, such as deploying new versions and configs, changing the visibility status of the world, etc. And using the control plane, worlds can add those instance hubs to their world. All of these are workflows, essentially state machines that are coordinating different actions that need to happen between them. So naturally, we use step functions to do this. Step functions provides an easy way for you to define a state machine, and it works great with serverless technologies, Lambda, DynamoDB, etc. So let me take a look at serverless. Of course, serverless doesn't mean that AWS is magically doing work without any servers. No, it just means that we, as customers, don't have to manage those instances. That means no OS patching to do, no maintenance. If an instance goes down, you don't have to be the one to worry about it. This makes it highly available and fault tolerant without you having to do anything. And serverless has built-in easy-to-use scaling, so you don't have to worry about the number of instances that you're using or the size of instance that you're using. It pretty much scales out of the box. But you should still always do scale testing to ensure that you can hit the target load that you expect. And with serverless, you only pay for what you actually use. So this is great if you're early in development or you have internal stages where you don't get regular usage. You don't have to pay for very much. You don't have instances sitting around pulling for data. Here are some of the services that are serverless in AWS. Now, with our step functions, we're triggering Lambda, but if you know Lambda, it has a maximum runtime of 15 minutes. And not all of our operations work that quickly. Deploying new server versions, for instance, takes a while. So you can use the asynchronous task token to pause your step function and resume it later when you're ready. Here's a simple diagram of what a step function with deploying your software might look like. So in the beginning of the step function, we'll tell code deploy to deploy the new server version to the instances, get an ID, and then we'll correlate that with our asynchronous task token in DynamoDB. When code deploy is done, we get a notification through SNS, SQS, and then Lambda handles this, grabs the asynchronous task token from DynamoDB, and tells the step function to finish. And it's great to notice that while we're waiting for this deployment to finish, we're paying for no costs because there's nothing waiting for, no instances pulling for that completion. So here we have the control plane. And like we said, we have the step functions, which are triggering Lambda. Lambda being stateless, stores state into DynamoDB, and calls other services. And ultimately, this all operates on worlds. Lastly, in front of our control plane, we have API gateway handling requests and triggering Lambdas to kick off those step functions. With this, and the powerful resources of AWS, we were able to scale from just over 2,000 instances at launch to over 5,300 instances among 486 worlds with an extra 25% buffer. That's adding thousands of instances because the player demand was far greater than we had anticipated. This is the power of our control plane and its value. So now we have the capability to create and manage hundreds of worlds, but there's still something missing. Before a client even connects to a world, it needs a certain amount of information. What characters are available to them? What worlds can you log into? How does it know which instance IP and port to connect to? That's where we have our microservices. If you're unfamiliar with the microservice architecture, the idea is that you have many different services, and each of them does one thing really well. It's contrasted against a single monolithic application, which tends to have messy code and trying to do all of this work in one place. With our microservices, we're able to encapsulate components of work outside of the server so that the server itself can be dedicated to handling the world's logic. And as mentioned earlier, the microservices allow our clients to communicate with the backend as a larger idea before they're even connected to a specific world. It even makes communicating with other parties easier, such as customer service asking for the data of a player or a world. Here are a list of some of our microservices, and we're always adding to this list. The backbone of our microservices are API Gateway, Lambda, and DynamoDB. Again, API Gateway handles RESTful requests from the internet with a single nifty URI like this, triggering Lambdas, and Lambdas storing that state in DynamoDB. From there, you can talk to other microservices, and other than this, you essentially have the whole world of AWS at your disposal, which if you've looked at that menu, there's a ton of services. And if you remember this diagram from just a bit ago, it actually kind of looks like our microservice diagram. Maybe you could consider the control plane one very important microservice. Now, I want to take a look at some of the microservices and show you how that works. The gateway service is one of the few services that our clients actually communicate with. It's kind of like the rep is for the worlds. It's the main point where we have to do authentication and security on. We do input validation here, and we can put AWS WAF in front of this to protect against DDoS attacks. The character service and the world service do the work that I had mentioned in the beginning, where the worlds and the control plane are writing the data to these services, and the clients, when they get to the main menu, can request the data from these services through the gateway service. And lastly, we have the channel service, which allows the clients to discover what endpoints they need to use to connect to the gateway service in the appropriate region. Now, all of this inevitably involves many resources. So we use CloudFormation to deploy all of our resources. CloudFormation is what we call infrastructure as code. So you define a JSON block or YAML block that describes all the resources that you want in your stack. This makes it easy to see what is involved in your stack in one place. Here's an example of a DynamoDB table, a simple DynamoDB table. If you were to create this in the console, this would involve a lot of clicking, a lot of copying and pasting, and probably be very error prone. Here's another example where I export the API Gateway URI from one CloudFormation stack and import it into another so that my Lambdas can know how to connect to the other microservices. Now again, all good servers and services need logs. For us, because we use Lambda, it goes directly into CloudWatch, which we can query using CloudWatch Insights, as I had talked about earlier. For our microservices, we do actually use CloudWatch for metrics, but we don't publish to the APIs. Instead, we use something called metric filters, which allows us to match patterns in our logs and publish to the CloudWatch metrics. But even better, there's something called the embedded metrics format for logging, which not only allows you to publish to the CloudWatch metrics, but allows you to create those metrics dynamically, to dimension them dynamically, which we weren't able to do with metric filters. And the great thing about these two metrics publishing methods is that we don't call any APIs for CloudWatch, which means we don't have to pay for anything and we don't have to worry about throttling. We do actually use CloudWatch also for dashboards, so you can view the health of your services all in one place. So now we've added CloudFormation here and CloudWatch. If we take a step back, we can look at all three of the pillars that we talked about. First, we talked about the worlds, how they're hosted on EC2, and how the network configuration is set up to protect the hubs from the internet. Then we talked about the control plane and how it allows us to manage all of our worlds simply. And lastly, we talked about the microservices, how they allow us to communicate with the client prior to connecting to any specific world. And because all of this is hosted in AWS, we can run our game in any region that AWS has these services. This made it easy for us to go from running in 2 regions to running in 5 worldwide. And trust me, your customers will love that they have servers near them. Now, of course, there's so much more to make New World run than just these 3 components. I'm not talking very much about alarms and ticketing or analytics or even the build, not to mention all the hard work that goes into the actual C++ server and client. But I hope this was able to give you a glimpse into how New World is built on AWS and inspire you to create great games for yourself. 감사합니다.